Log on, tune in, find out. Another good idea from Cambridge.
The speaker this morning is Alfred Ramani. He's going to talk on the Deautonomising integral non-QRT mapping.
Well, first I want to thank the organizer for inviting me to this beautiful place. This work has been done with a lot of collaborators over some years. So the QRT mapping is very interesting integrable discrete systems which have been introduced by Quispel, Robert Thompson quite some years ago. It contains effectively 5 parameters, and it's a second order mapping for so for one variable second order mapping for one variable in terms of 2 ancestors, and it has an invariant in terms of only 2 instances of the variable, and so the equation just written by the difference between this quantity at 2 instances, and you get this equation. And the solution of this mapping is reasonably simple. Up to a homography, it's an elliptic function sampled over equidistant point. Well, you could call it translation over an elliptic curve if you want to use fancy words. Now, there's an 8-parameter system which generalizes this system in terms of 2 equations for 2 variables. So every other equation is identical to all the odd equations look alike, or the even equation look alike. So in fact, you can separate the even and odd variables, and you get a system which contains 8 effective parameters. And both those systems satisfy two properties which have been associated to integrable discrete mappings, which is that they have confined singularities. That is, if you hit an infinite at some point, instead of recurring infinites forever, after a few steps, you got a regular behavior again, which is not the generic situation. When you write any random system, you won't have this property. And also it has 0 algebraic entropies. If you write the variables as a rational function of some initial value, the degree growth of the rational functions is only polynomial and not exponential, and this is also a property of discrete integrable systems, of integrable discrete system, I should say. The point is, for a long time, we were so used to work only with these QRT systems that we even wondered whether there were any discrete systems that were interesting which were not within this parameterization. And in fact, some years ago, Hirota, Kimura, and Yahagi found second-order mappings where the invariants were not a ratio of quadratic polynomial, but of quartic polynomial. Maybe I didn't attract your attention. Here, the invariant is quadratic in each of the variables. And this is also true in the case of the asymmetric QRT system. It's always only quadratic in the variables, while in the Hirota, Kimura, Yahagi, the invariant is quartic. And after this original work, several systems of the same kind were found. Now, why I'm speaking of deautonomization? Because the QRT mapping doesn't contain the independent variable explicitly. It only enters through the index of the dependent variable, but there's no explicit dependence of the equation in terms of independent variable. But if you try to change it a little bit by allowing the independent variable to enter the equation, what you find is what were called the discrete Palvé equation. That is, integrable equations, integrable discrete systems, which contain explicitly the independent variables, so we call them non-autonomous, which are integrable, and the continuous limit of which are Palvé equations. So they were called the discrete Palvé equation, and a lot of developments have been done with them, and all came from deautonomizing the symmetric and the asymmetric QRT mapping. So if we have now new systems which instead of having biquadratic invariance have biquartic, question is, will it be interesting to de-autonomize them? What kind of new non-autonomous discrete systems can we get? So first I have to show you what those systems are. The first one, which were found by Hirota, Kimura, and Yahagi, was this one. And if we start with x as a ratio, some rational function, then you see the degree grows only quadratically, which means this is integrable. If you change anything here, you'll find the growth will be exponential. So the fact that the growth here is only quadratic means this system is really special and integrable. And in fact, it has this integral. This is just written for convenience, otherwise it will be too long. So, but as you see, now this, because it's a square here, well, it's a product, it's quartic. So this is not in the QRT family, but it's extremely close. I mean, it looks very much like a QRT mapping, but not quite. So it's nicer to change the variable to this form. And now this looks very much like what is an instance of the QP5 family. So from a QRT mapping that looks very much like this one, we found that you could de-autonomize it, introduce an explicitly the independent variable n to find an equation that goes to P5. So this is really, it looks very much like a P5 instance, but not quite. Why not quite? Because if you look the way the singularities go, if you enter the singularity by P here, so by making this infinite, then in the Hirota, Kimura, Yahagi case, you exit by the same singularity. If you had come with -1 over P, you'd come with -1 over P. While in the QP5 family, if you enter by this singularity, you exit by this one. So somehow, the fact that you come out by the same singularity rather than exchanging singularities distinguishes the regular QRT case with biquadratic invariance from this one which has biquartic. And this seems to be some characteristic. So now how can we get this equation? If you start now from the full non-autonomous Pareto-5 equation, which is here, well, it's asymmetric QP5, so in fact it's a P6, but I won't get into detail. Anyway, this is the most general equation we can write de-autonomize with a full dependence q to the n here. Now we ask, how is it possible for this system not to be explicitly n-dependent? Now, if q is 1, well, this is trivially q. We are back to the trivial QRT case. If q is -1 and p is -r and s is -t, then the qn terms disappear. You have only q to the 2n, but q is -1. So that would mean that the denominator would not explicitly depend on q if we take q is -1. Then you'd say, well, back to the original case. No, we are not back to the original case, because in order for this to be integrable, you need this condition. And if q is -1, well, the condition is not the same as if q is 1. So the fact that q is -1 can be seen from here. And you get a different equation when q is -1, even if p is -r, s is -q, s is -t. You don't see q to the n at all here. But the fact that st is -1, you get something different. So in fact, what I've done here is there should have been a plus here, but I absorbed it by change of variable to put the I in the x instead of the. So I change it here so it looks like the same hasn't changed. But then because of the change of variable, the product here is -1 now, when it used to be 1 here. So this equation is not the same as this one with q is 1. This is a different equation, and it is exactly the, by the change x is 1 over x. This is the original equation written by Hirota, Kimura, and Yahagi. It's, with the product here is -1, when in the QRT case you need the product to be +1. And this has a quartic invariant. Now, you might say, if I take this one, I de-autonomize it, what do I get? Well, I get back here. So starting from this equation and going back won't teach me much. But it gives me an idea that such equations do exist, and we could look for them and find more results. So there's another, instead of starting from P5, we can start from P4 and get this system, which also has biquartic invariant. Now, I should say something. The fact that it has a biquartic invariant per se would not guarantee integrability. The existence in the discrete setting is just the existence of an invariant need not suffice to prove integrability. But we know those equations are integrable indeed. Why are they integrable? First, they are limiting cases of Pauli equations when the dependence on the independent variable is almost trivial. If the dependence was absent, Q is 1, Qn doesn't appear at all, then they are QRT, and we know that the quadratic QRT invariant is enough for integrability. If Q is minus is any number, not a root of unity, then I have a genuine discrete Pauli equation. But we know that those are integrable in, well, the way they are integrable is more complex. The notion of integrability for non-autonomous Pauli equation is much more complicated than for a autonomous discrete system. But they are considered as integrable, well, because the way they behave. So certainly this will not be less integrable than a Pauli equation. But in what sense, more precisely, we can say it's integrable? This one, and also, for instance, this third one, which is also of the same kind. So the fact that they are integrable is not just because they have this quartic integral, but because themselves they are just addition on elliptic curve in a sense. However, the structure is it has been described by someone by we go from one elliptic curve to another one. So in fact, all the even instances are on one elliptic curve and all the odds are in another one. But there can be a simpler way to interpret this, because if you allow for homography, a different homography for the even and the odd, in fact it's all a single elliptic curve you're on, but instead of having always the same addition, you have two different addition of alternating quantities. That you from even to odd you move by one quantity, from odd to even you move by a different quantity. So it's still an addition, but an addition with alternating, not opposite, of course. So when you do it twice, it's just an addition, but it's even each step is an addition, but with alternating quantities. So it's really a single elliptic curve you're working on. You don't really need to describe two different elliptic curves. So again, all those cases, I just gave them examples, because if you, just to show you what kind of non-QRT discrete system you can have. But there's no point in deautonomizing them, because they all came from taking a Pauli equation and making it look like it's autonomous by taking Q is -1 and hiding the Q to the n terms, keeping only the Q to the 2n. So this won't give you new systems, but this gives you an idea of what the new system should look like that you want to study. So now we have studied completely different new systems, which also are not QRT, but have higher invariance. Sometimes quartic, sometimes even higher than quartic, which are written first in autonomous form, and then we wonder, what if we try to put explicitly the independent variable in it? Do we get new interesting systems? So I'm going to describe two classes of systems. the first class is inspired by the discrete Palovay equation, but in a somehow twisted form. That is, instead of taking here the product of xn minus 1 to xn plus 1, which would be the third Palovay, the third discrete Palovay equation with the right-hand side, we put this on. We move xn minus 1 from the left-hand side to the right-hand side. And we study this kind of systems. So then P and Q should be polynomial of degree not higher than 2 if we expect integrability. So first try linear top and bottom. And in order to find which integrable system, which of those systems are integrable, we apply the singularity confinement. We assume we hit the singularity and demand that singularity stops after some steps. So if you try it on here, then you find that you don't get anything interesting. Now the point is that the singularity confinement was originally proposed as a necessary and sufficient condition of integrability. And in fact has been found that it's neither necessary nor sufficient. So you can have integral cases which are not confined and confined cases which are not integrable. Still, it's an extremely useful tool. It's, let's say, neither necessary nor sufficient, but extremely useful. So in this case, well, I'll show you how useful it is. In this case, if you demand singularity top and bottom, if you demand singularity for both possibilities, I start from the bottom or I start from the top, you get nothing interesting. So you could ask, what if I ask only one condition of integrability, or of confinement? I ask only for one confinement. Well, if I violate both confinement conditions, indeed, you find the algebraic entropy is positive and the mapping is not integrable. So violating both conditions indeed leads you to non-integrability. So you see that the conditions were interesting. You learned something by asking for them. But if you satisfy one of them and violate the other one, turns out the algebraic entropy is still 0. So you have an integrable system with 0 algebraic entropy, which is not confined. Well, we've known for years that such systems exist. And in addition, because since the degree of the iterates doesn't grow quadratically, as is the case with the Palovay equation, but only linearly, then we know that the system is simpler. It should really be linearizable. And in fact, whenever we have an integrable system which violates single confinement, it cannot be of Palovay type. It has to be linearizable. It's a signature of integrable systems which violate singularity confinement that they must be linearizable. So this will be a linearizable system, 0 entropy but non-confined, and this is a linearization. We introduce this variable y, and then we realize that y must satisfy a linear equation with a non-homogeneous linear equation, and once you know y, you can solve for this. This is just a homographic discrete Riccati. So we've broken down the second order equation for x into two first order equations, one for y, and once you have solved for y, then the first order equation for x in terms of y, which is what we call the Gambier, a typical Gambier equation, discrete Gambier. It would be the generic case of discrete Gambier is that you solve here a homographic equation, not a linear but homographic equation for y, and once you have y, you solve the homographic for x in terms of y. This is the Gambier discrete map, which has been called this way because this is the class of Palovay equations which Palovay didn't study, but in fact his student Gambier studied in the continuous case. Among the 50 standard cases of equations supposedly classified by Palovay, one Palovay did not do at all. Its student Gambier did it, and this is so you have two Riccati equation cascade. You solve a Riccati equation for an auxiliary variable y, then a Riccati equation for x in terms of y. This is a way to get integrable equations, the continuous case, and this is the analogous in the discrete case. So I'm going to speak very much about Gambier map in the remaining of my talk. So anyway, that equation, when one confinement condition satisfied but not the other, can be reduced, can be linearized through a Gambier map, and does not satisfy singularity confinement. Okay, now this is a very amusing case where when we try to apply singularity confinement on this form, well, first you have to put D 0, and then if D is 0, you find two patterns which terminate, which means that you do, in that case, have singularity confinement, but it's not integrable. So the same example furnished us with one case which is integrable by linearization without the Palvé without the singularity confinement, and one case which is singularity confined, but is not integrable. And what is very strange, so this is a mapping. So the mapping of this form have been found by Yetarinta and Vialet some time ago, but those were found by Yetarinta and Vialet violated a very simple condition of de van Linne theory, because the ratio here was at a pretty high degree, and it could be shown rather easily that no integrable equation could have this form, because the polynomial, the rational function had too high degrees. But in this case, if you see that if you write x n plus 1 over x n minus 1, the right hand side has only second degree on top and bottom, well, and even further bottom. So there's no immediate reason why this cannot be integrable. It's a pretty very interesting case of non-integral mapping, but I'm completely out of my topic. I want to talk to you about integral mapping, so this is just an aside, but it's a very amusing equation, this one. I will have to do more about it. Anyway, now I'm going to the most interesting case where you have quadratic top and bottom here. Then you have to do the singularity confinement pretty carefully, and when you do that, you find three cases. You find three cases, and you can see that the third one, well, if you just call a variable the square of, if you just take the square of it and call the square of variable, give it a new name, you recover exactly this one with alpha is minus 1. So this is somehow equivalent to the subcase of this one. Those two are different. So all those three cases have zero algebraic entropy, the quadratic growth of degree of the iterate, so they are non-linearizable, and they have higher degree invariance. So they do belong to the Hirota, Kimura, Yahagi class. So here are the invariants. So what I'm writing is not the invariant. This is some kind of pre-invariant. In this case, the invariant is the square of this quantity. In this case, the invariant is the fourth power of this quantity. So the invariant is degree 8. And here it's also the degree 4, but if you notice, we already have quartic here. So globally, here the invariant is degree 16. Well, pretty nice. So, well, the deautonomization, in the linear over linear, we knew it was linearizable, so we just managed to show that you can introduce a free function. So Cn can be a completely free function. Bn is determined in terms of C. And so here you get a linearizable mapping containing a free function, which is typical. Usually when we have a mapping which is linearizable, you can introduce a completely free function into it. So this is a rather standard case. This case is more funny because, well, when you try to allow A, B, C, D, F to depend on the independent variable n, well, first the calculation get out of hand. So first you use a gauge on x to put A to 1 to make the calculation manageable. And then you get all this. And this is curious because it's not very common to have a power n square minus 1. This is a pretty unusual feature. But then what you do after you put A to 1 to to be able to manage the calculation, then you say, no, no, it's too ugly. So I'm putting back all this into the definition of x, and then those a, b, c, d won't have those ugly terms. They simplify a little bit. So I'll show you next page what this equation looks like. That's already bad enough. That's what you get when you absorb the first term in. So you recreated the a, of course, by absorbing the main factor into the x, and you get this. And when you get this, then you think about something. What about trying to put back x on the other side now? Now you can do it, but you cannot change even and odd. You have to do something more complicated. Out of 4, you keep 2, you invert 2. So 4k plus 0, you keep the same. 4k plus 1, you keep the same. 4k plus 2 or 4k plus 3, which is 4k minus 1, you invert the variable. So you define a new variable y by this. And lo and behold, you get something you knew already. Unfortunately, all this complicated situation, finally, after all the change of variables, we got an equation we knew. This is the asymmetric P3 discrete Paul-Levé equation that's been known since in fact, it was originally written by us very, very long ago, but at that time, we didn't realize exactly what this equation was. And it's Jimbo and Sakai which discovered that, in fact, this is a discretization of the Paul-Levé 6 equation. But we, except for the continuous limit being P6, we have written about the equation even long before Jimbo and Sakai. Okay, so now this is what happened when I tortured the poor P3 equation. Now I'm going to torture the poor P4 equation. So the Paul-Levé 4 equation has the product of those two terms with the right-hand side. And so now I use the ratio of those two terms, and I look at that. And in fact, the only integrable case is linearizable through a Gambier mapping. So it's not so interesting. Well, what is amusing is that because the Gambier mapping that is used to linearize it is just this. This means that you can write some kind of a transcendental conserved quantity by taking the tangent of yn. So here we have an equation which has a transcendental conserved quantity, which is a pretty amusing result. And when you deautonomize it, well, again, because it was linearizable, you can introduce a completely free function g. And I introduce g here because it's easier to express a as a differential of g. And this is how you deautonomize this equation with a free function g. And this is a subcase. So no, this was no. I mean, if instead of taking the right-hand side by quadratic over quadratic, I take linear over linear, then I get a different calculation, which is not included in the first one, and I get this. But it's also only linear growth, so it's linearizable, reduced to a Gambier equation, and contain the free function g. Now, the same game can be played for poor P5 equation. Instead of taking the product, I take the ratio. I look at the right-hand side, and I find only one integrable case, where C and D can be expressed in terms of A and B. And again, it's linearizable. And because the equation for y, which is used in the Gambier mapping, is that simple, if, but only if, lambda is a root of unity, I can get here an integral which is just y to the p, which, depending on the value of lambda, can be of arbitrary degree. I mean, of course, the lowest possible p is arbitrarily high depending on lambda. So this is also a pretty interesting result, having integrals of arbitrary degree here. And again, I can look how I can make this non-autonomous. And since it was linearizable, I expect a free function. Now, if I just look at a and b constant, I get nothing here, of course. But what I called autonomous case in the previous slide corresponds to a and bn as proportional to lambda to the n, and you get exactly the lambdas placed where I wrote them on the previous page. And again, you have for arbitrary function b, now you have a Gambier mapping linearization, and which can simplify to this case in different cases. Okay, so now I've finished the class of systems obtained by torturing Pain-Levé equations, which in fact led only to linearizable systems when you try to deautonomize them. And now I'm going to go to the last part of my talk, which deals with a different class of systems, which were written autonomous to start with, and we try to deautonomize. So we started from the Adler-Bobenko-Suris class of integrable lattice equation that they found by consistency around the cube. So they had three classes of equation: the A list, the H list, and the Q list. And today I'm going to restrict myself to the Q list only. So this is, so on a lattice you have those four equations: Q1, Q2, Q3, and Q4. Where Q4, they wrote it originally in a pretty complicated way, which has been simplified by Yetarinta. And in fact, it turns out that this here alpha and beta are constants. It turns out that this way of writing it is extremely useful for what I'm going to do later. However, let me point out immediately that in fact, A, B, if I call this A, B, C, D, and E, I can use any values of A, B, C, D, and D, and it will still be integrable. The fact that this is a Sn, and of all those Sn must be understood as having K as a parameter, but in fact it's completely generic. You put any numbers here, you can solve an equation for K square asking, is it possible to have alpha beta such that this is, of course, you have one global factor. You can multiply your equation by a global factor. So I'm not saying if I put A, B, C, D, E, I can solve it for those values, but I multiply by global factors. There will always be a K square such that up to a global factor, I can write it like this. Just count how many equations you have, how many unknowns you have, and this. You can always write it like this for any prefactors completely. So anyway, those four equations follow degeneration cascade. So now those are equations on lattice. I'm talking about discrete equation on a line for n. So in order to what I have to do is make reduction. So the simplest reduction is to identify the shift in m with a shift in n, and see what happens. Well, Q1 is a very simple equation. This shift is a very simple one. It completely collapses. This presents absolutely no interest. So in the case of Q1, which is so simple, I'm going to use a more complicated reduction. So a shift of 1 unit in m is like a shift of 2 units in n. And then I get this equation. However, it turns out this is just a QRT mapping. So, well, it's a nice equation, but, well, just QRT, so it's out of my interest of today. But one thing is important. What does it show? It shows that even the simplest equation of ABS, the Q1, is not linearizable. If it were linearizable, then any reduction should be linearizable. But this is a reduction which gives me a QRT mapping which is not linearizable. This has a quadratic growth of the iterates. So which shows that clearly even the Q1 equation and a fortiori the higher ones are not linearizable equations. Definitely not. It's only, but in the case of Q2, since this mapping, now I'm going back to the simplest reduction. The shift in 1 unit in m is only 1 unit in n. So this is a pretty trivial shift in a sense. And this equation will, as you'll see, is simpler than it looks. Well, first, it's not QRT. If it doesn't have a biquadratic invariant. If we construct this quantity, which I can call a pre-invariant, you can see that at each stage, instead of being constant, this quantity is transformed into something which is proportional to its inverse, which means that this quantity is constant. So k becomes ab squared, okay, but this curly k is a constant. But this curly k, of course, is not biquadratic, it's biquartic. So I found a biquartic invariant for this mapping. So this is a non-QRT mapping. It's a HKY type mapping. Now, what we found out is that it's very interesting, in order to understand what kind of mapping this is, to pretend, well, not to pretend, but to investigate what is the QRT mapping that would have this pre-invariant. So in order to study this, the mapping which keeps this invariant, but where k is changed into its inverse, proportionally inverse, to understand the structure, we study the QRT mapping where just k is kept invariant, and see what does this mapping look like. And this will tell us something about this one. It's a way to extract information. And it turned out that this QRT mapping is not just any QRT mapping, it's a linearizable case. We recognize it immediately because it's in our, this is a mapping which we are used to see. So we recognize it immediately as a linearizable case. And it's so simple that in fact you can have the general solution of this mapping. So going back to our original mapping, which is not QRT but has quartic invariant, we were wondering, well, if this one is linearizable, wouldn't this one be linearizable too? And it turns out that yes, it is linearizable. You just upshift it, make the difference, define this quantity, and write in terms of this. And this equation for y itself can be solved, is linearizable in terms of Gambier mapping, in terms of the new variable z, which is just linear. So you can solve for y, and once you have y, you can also solve for x. And so it turns out its solution for x is not much more complicated. Well, it's ugly enough that I didn't want to write it, but it's not very, very much complicated than this. So we can solve completely this mapping. So Q2 is just a linearizable mapping which can be explicitly solved. Now, Q3. Again, we use simplest reduction. A shift in m is just a shift in n, and this is what we get. And again, we found that there's a pre-invariant, which is quadratic over quadratic, but it's not an invariant. It goes to its opposite. So the only invariant is a square of this quantity. So this is, again, a HQI mapping with a quartic invariant. And again, well, this is the so maybe I jumped the intermediate case. First we studied what would be the QRT mapping obtained by asking that k is completely conserved. Then this would be a QRT mapping. And again, this QRT mapping was found to be integrable, to be linearizable. So if the QRT mapping by keeping k constant is linearizable, then we assumed that the mapping, the original mapping, the one where k is changed to minus k, would also be linearizable by it's not a proof, but it was logical to look for it, and we found it was. So again, this mapping here can be linearizable through a Gambier map. Now, as I said repeatedly, whenever a system is integrable by linearization, you expect it to contain a free function. But in this case, you cannot, well, if you look what the system was originally, the factor here I have a constant factor which I can allow to be to vary with n if I look for deautonomization, but the ratio here is 1. So a 1 seems to be independent of n, whatever n is. But if you try to find a deautonomization of this mapping with keeping those two coefficients equal, then you find a case, you find cases, but you don't have a free functions. You find cases depend on an explicit function, not a free function. So this worried us for a while, and we said, okay, so let's give more freedom. So now we allow A and C to be two different functions of n. And if we do that, then we manage to write again a linearization of this equation in terms of a Gambier mapping, all in terms of a free function, completely free function g of n. But of course, if g is generic, this equation will be integrable, but A and C would have different values. In order for A and C to be equal, you have to put some extra constraint on g, which is what I was telling you before. We can extend this with some function of n while keeping A and C equal, but then it's not a generic function. It's a specific function of n. So, okay. So, well, anyways, those are what we need in order to linearize our system, and asking for C to be equal to A gives a pretty complicated equation for G, which, however, we know how to. We have the general solution for G, which keeps C equal to A. So we have again found a deautonomization of the reduction of G3, but once again it's linearizable, so it's not so fantastic. But now I'm getting to the most interesting case, the case of Q4. Now this one was really very, very nice. First, we write with alpha and beta constant, and again we find that there's a quartic invariant which can be obtained by a quadratic pre-invariant. So this is quadratic, and but when you iterate, it goes with opposite. So the only invariant is the square of this with this quartic. So again, in order to understand what's going on, we are going to study what is the QRT mapping obtained by asking for this invariant to be constant, not to change sign. And in that case, you find that the invariant curve is a genuine elliptic curve, not like in the case of Q3. In the case of Q3, you got only a conic section. This was a signature that the system was linearizable. Whether the original quartic or the degenerate QRT system we studied were both linearizable because the elliptic curve degenerated. But in this case, this is a genuine elliptic curve. So this is not linearizable. You have one signature is if you look at the iterates in terms of rational functions, the degree of the rational functions grow quadratically, not linearly. So this is a real integrable system, non-linearizable. In a sense, it's a Pain-Levé type integrable system. It's a rich integrable system. So so now I'm still in the autonomous case. I'm still in the autonomous case, and I'm going to study the singularity pattern of the autonomous case. In order to be able to make it non-autonomous, I have to understand what is the singularity structure in the autonomous case, so I can reproduce it in the non-autonomous to find how should I make it non-autonomous. So we make a change of variable. Well, this is just a change. These are just names, okay? I just call gammas, they have sum, and these have difference. It's just by hindsight that I called one gamma and the other z, but this is completely general. It's just a name, okay? So this equation just becomes this by changing the names of alpha and beta to this. And then singularity means that I start with xn and x minus 1, and xn plus 1 is independent of x minus 1. This is a singularity. When I lose degree of information. When does this happen? When does xn plus 1 be independent of xn minus 1? When is a singularity? When x is either this quantity or that quantity. I mean either this quantity or that quantity. And if that's true, then xn plus 1 loses information on xn minus 1 and takes these values. And then xn plus 2, of course, it's it doesn't know what xn plus 1 is. It's just equal to xn. And when you try to compute xn plus 3, you find 0 over 0. Which means that this is how the singularity is confined. The information of x minus 1 that was lost on xn plus 1 and xn plus 2 reappears at xn plus 3 as 0 over 0. And if you follow, if n of taking this exactly, you take it very close to, you take it equal to this plus some very small quantity, and you iterate, then you find that the 0 over 0 is in fact determined at the limit of a small quantity, and the information that seemed to be lost is recovered. So this is how this is singularity confinement, how you recover the information. The 0 over 0 gives you back the lost information if you're careful. So this is how, so I enter by C over D, by C over D of the Z quantity, or C over D with, or D over C with 1k here. Those two quantities is what enters the singularity and also exits the singularity. And in the middle, I have C over D of this gamma. So now I'm going to do the same for the non-autonomous case, right? I assume that Zn and gamma n depend on n. So I enter by xn having those values in terms of Zn. But when I compute xn plus 1, I see that it depends on gamma of n, not gamma of n plus 1. If I have to do the calculation carefully, I see that this depends on gamma of n. Now, in order to exit, I entered by xn is C over D of n, of the n. This has to be C over D of the n plus 2. But in order for that, if here I have C over D of n plus 2, that means here I must have C over D of gamma n plus 2. So one condition, in order for all this to fit, then gamma must be, gamma of n plus 2 must be gamma of n. So I have only, but I have some freedom. The even must be equal, the odd must be equal, but I can have two different values at even and odd. So already I have a freedom that I didn't have originally. Gamma must be, all the even must be equal, all the odd must be equal, but I can have two different quantities. But that's not enough. I also want the equation to make sense. That is, I must go from this quantity to that quantity using this, and it must be true. So I have one more equation to write. And not only one, I have to write 4, because x could come with plus or minus sign, but I could also take dn over cn instead of, well, 1 over k dn over cn instead of cn over dn. Now, the something which we realized is that those quantities are, in fact, exactly essence moved by quarter periods. The ratio of two elliptic functions is not any other two elliptic functions, but it turns out those two quantities are exactly this one and exactly that one are just essence shifted by quarter periods. So what we have to solve is this equation to say that this value and this value fit with this value in the middle. And this equation, in fact, is the same for all 4 values. Even though here I have C over D and dC over K, I have the same equation, and moreover, the even and the odd appear symmetric. Even though they enter originally in complete different ways, they end up symmetrically here. So this, I have only one equation for all 4 possibilities, which is of this form. And more precisely, this is one possible solution. So the solution is just z advances by the sum of the even and odd gammas, and the y is just an Sn of this quantity. Now, the point is, if you count the number, this looks like it's pretty well defined, but in fact, if you count the number of unknowns, you realize that in fact k is free. I mean, since the entire equation can be multiplied by a global factor, a and b and c are not really known. Only the ratio b over a, c over a are known. And if I multiply them by any number, I can always solve this equation for any value of k. So this means that in fact, this solution here is really true for any value of p. I mean, I have 4 degrees of freedom here. Well, I have gamma 0, gamma even. No, I have q, p, and omega here. So this system, I can take those elliptic function of any value of k I want. Now, the degree growth integral, as I said, is quadratic, and so this equation is non-linearizable, integrable, but non-linearizable. Now, this is, if I go back to here, you see that in this equation, those are just alternating sign, but here you have actual elliptic functions of variables that explicitly depend on m. Explicitly depend on n here. Now, this is a Paul-Levé equation where the variable depends as an elliptic function of the independent variable. This is by no means a trivial case. We've known for quite some years that such equations existed. I mean, in Sakai thesis, he predicted that such equation should exist. I mean, he wrote a way to obtain them, but none were explicitly written for. He didn't write them explicitly; just gave the way how to construct them. Some years ago, we wrote an explicit case of elliptic function of Paul-Levé equation containing explicitly the n variables through elliptic function, but it was pretty ugly. This one is extremely beautiful. It's the first beautiful elliptic Paul-Levé equation ever written. The first that fits in 2 lines, essentially. The other one need half a page. And it's certainly the first that has been obtained as the deautonomization of a reduction of a lattice equation. So in that sense, it's pretty unique. I think it's very, very beautiful, and I wish we were able to see exactly where in the Sakai scheme it fits. It will need some more investigation. But this is a very, very nice equation, which we are very happy to have found. Thank you.
Any questions?
How many parameters do you have in this equation? How many parameters?
Well, gamma z. Well, we have 2 gammas, even odd. The step is gamma 0 plus gamma odd, so the step is not free. Then you have the 0 point of z. I mean, z has a 0, so we have 2, 3, and k, no, 4 parameters. Gamma 0, gamma even, k, and the shift and the 0 point of z.
Any other questions or comments? I just a minute to thank Alfred again.